Hello, everyone. Thank you very much for joining us in today's webinar. My name is Braden McNeil. I'm the Technical Sales and Marketing Lead here at Aquanty. I do believe I've been in contact with almost everyone in the meeting today, but in case you have any follow-up questions about HydroGeoSphere or Aquanty, feel free to reach out to me anytime. My email is bmcneil@aquanty.com, and I'll include that in the chat in just a moment here. I'll take a moment just to introduce today's speakers. We'll be starting with a presentation by Dr. Peter Forsyth, Professor Emeritus at the Cheriton School of Computer Science at the University of Waterloo. Before joining the university in 1987, Dr. Forsyth was a senior simulation scientist with the Computer Modeling Group and president of Dynamic Reservoir Systems, both based in Calgary. Both positions involved development of software for reservoir simulation, including multi-phase subsurface flow and transport. Peter has collaborated with Ed Siddiqui and René Terrien for many years, developing efficient numerical algorithms for nonlinear partial differential equations and sparse matrix solvers, the very same algorithms that now power HydroGeoSphere. In 2012, Dr. Forsyth joined Dr. Siddiqui and Terrien in founding Aquanty, and to this day he sits on our board of directors. And today, Dr. Forsyth will provide a general review of the control volume finite element method and associated concepts, including monotonicity, mass conservation, and the sparse matrix solver that's embedded in HydroGeoSphere. Following Dr. Forsyth's review of finite element solution techniques, Dr. Hyoun-Tae Hwang will review the numerical schemes related to mesh grids and the parallel computing capabilities provided by HydroGeoSphere. Dr. Hwang is the director of HydroGeoSphere and a senior hydrogeologist at Aquanty. During his PhD at the University of Waterloo, he was involved in several projects relating to developing algorithms for numerical simulations, including HydroGeoSphere, a fracture network generator, and multi-phase isotope fractionation for CompFlow Bio. His research interests are in the areas of parallel computing, integrated climate and hydrological simulations, as well as global scale hydrologic simulations. Dr. Hwang was one of Aquanty's first employees, officially joining the company in January of 2013. So he will review the flexible parallel computing capabilities provided by HydroGeoSphere using the OpenMP framework. Fully integrated hydrologic simulations, such as those performed with HydroGeoSphere, involve highly nonlinear processes, and therefore the computational efficiency of the model becomes a critical issue when performing simulations. With that in mind, we're constantly looking for ways to increase the computational efficiency of HydroGeoSphere, and parallelization is one big part of that effort. The HGS parallelization framework allows the same code to be executed on various shared memory platforms with minimal maintenance and provides a flexible methodology for the efficient construction of the coefficient and Jacobian matrices. Okay, so with no further ado, we have actually pre-recorded the presentations, and so we're going to start with a recording of Dr. Forsyth's talk, followed by Dr. Hwang's. And we'll take a short break in between these two videos to take any questions. So as I said before, feel free to pop those questions in the chat as they come up.
Good afternoon, everyone. I'm Peter Forsyth. I'm a professor emeritus from the Cheriton School of Computer Science at the University of Waterloo. About 30 years ago, I started working with Ed Siddiqui on numerical methods for solving subsurface and surface water flow equations. And on the basis of that, Ed and his partner René Terrien and myself incorporated these ideas in some very early versions of HydroGeoSphere. So what I'm going to talk about this afternoon are some basic discretization techniques that we use in HydroGeoSphere, or HGS, as we call it. Now, a little bit of an overview of what we're going to talk about today is that I will talk about control volume finite element methods, which I'm going to denote by CVFE, FE for short. And the main thing about these techniques is they are mass conservative. They always ensure that the flow is in the physically correct direction. And they are monotone, which means we get no physically incorrect oscillations. And after I'm done giving you sort of a little more theoretical approach to this subject, Hyoun-Tae will tell you some more practical aspects, which involve things like mesh construction for CVFE methods and parallelization. Now, the control volume finite element method, or CVFE, BE for short. Basically, we use that to convert the PDEs in HGS, things like Richard's equation and the overland flow equation, into discretized algebraic equations. So why do we want to use CVFE? Well, this combines the best properties of finite element methods. In other words, we can use unstructured meshes, and finite volume methods, which are inherently mass conservative. So the objective in this presentation is to give you an informal derivation of the CVFE equations. And I will show to you that we get exact mass conservation for any mesh in any time step. We'll also preserve physically correct flow directions for any mesh at any time step. And the discretized equations are monotone. In other words, we get no spurious oscillations. And again, I'll point out I've used this same keyword several times here for any mesh in any time step, not just in some theoretical limit of vanishingly small mesh size and time step. So first of all, we'll think of looking at our equations in terms of a discrete mesh, right? So we define a mesh, and we'll look at a generic node I, and it will have a bunch of neighbors. And I'll be using node J as a sort of generic neighbor of node I, a mesh neighbor. We will make no assumptions about the mesh, the type of mesh used. It could be linear basis functions on triangles, or prisms in 3D, or tetrahedra. And we don't really have any assumptions about dimensionality, 1, 2, or 3D, or the order of the basis functions we use. And the same idea is used for subsurface equations, surface equations, fractures, double porosity, and so on. This is a very generic technique that can be used with wide applicability. So as a prototype, to give you an example of how we discretize the equations, let's look at Richard's equations. And where I'm sure you're all familiar with Richard's equations. So the left-hand side here, I have what I call the accumulation term, which is really just the time derivative of the mass accumulation at a particular point in space. And define some of these terms in the equation here. Theta here is, of course, the porosity. And S sub W is the saturation, the water saturation. And the right-hand side here, I have what I call the flow term. And the flow term has the absolute permeability in there. It has the relative permeability, K sub R. And it has the hydraulic head. And of course, the right-hand side, what you get is the gradient of the hydraulic head. And finally, we have some source sink terms. Okay, so accumulation, flow, and source sink. Now, I'll remind you of sort of the properties of finite element basis functions. These are just interpolants, if you like. So given a mesh, which is a bunch of discrete nodal values, at each node, we define what we call finite element basis functions. And these basis functions or interpolants have the following properties. So n sub I, the basis function associated with node I, is 1 at node I and 0 at all other nodes. And the sum over all the nodes of the basis functions equals 1 everywhere. And the right-hand side here, I've got a little right-hand side, the slide here, I've got the examples of one-dimensional basis functions, linear basis functions, also called hat functions. And you can see in that case that basically the basis function associated with node I, so xi is node I, say, so ni is the basis function associated with that node. It has a property that it's equal to 1 at node I and 0 at all other nodes. And so, for example, if hj is the value, the approximate value of the head at node I, then if I look at this expression here, I can approximate h, the hydraulic head, everywhere by just multiplying the nodal value times the basis function and summing that, and that will be our approximate value of the hydraulic head, which is true everywhere in the domain. It's just a linear interpolant over these basis functions. Now, how do we approximate the solution using these basis function interpolants? Well, let's let hjn be the approximate value of the head at node j time step tn, or n delta t. And again, we're going to approximate the hydraulic head, porosity times saturation, which is essentially the mass, and the source sink term at time step n, which is n delta t, by the following. So h, We'll approximate it by the sum over all the basis functions of the nodal value at time n, node j, times the appropriate basis function. And similarly with porosity times saturation, we'll multiply that by, so the porosity times the saturation at node j times the basis function, sum over all the nodes. That will then give us the approximate value of this expression everywhere in the domain. And similarly, the source sink term, same idea, multiply by the nodal value of the source sink term times the basis function and sum over all the nodes. Now, if I look at the exact solution of Richard's equation, we just move everything over to the left-hand side of Richard's equation. And what that really says is this expression here equals 0. Well, if we have an approximate solution to Richard's equation, now this expression here won't exactly be equal to 0. There'll be some error involved. The Galerkin approach is to make the error orthogonal to all the basis functions. So here's my approximate solution. And what I do is I multiply by the basis function associated with node I, integrate over the whole domain, and set that to be equal to 0. And I will repeat that operation for all the nodes in my domain. And that's the way we generate an approximate solution. So the first thing we do is do a very simple thing for the accumulation and source terms. We're going to use what's called mass lumping. And we'll use a fully implicit discretization in terms of time. So the accumulation term, then, if you remember what that looks like, multiplied by the basis function and integrated over the volume, I just pull this time derivative outside the integral sign and approximate that by a backward difference. And what's left over here, the integral of the basis function over the volume, over the whole volume of the whole region, is I'll just represent that or call that the volume associated with node I. So again, the volume associated with node I is the integral of the basis function at node I over the entire volume. So here's the accumulation term finally then, backward difference, right? Saturation times porosity at n+1 minus saturation porosity at time n divided by delta T times the volume. And similarly, exactly similarly, for the source term, I just represent that by the source value, the source term value at node I times n+1 times the volume. Now, more interestingly, is the flow term. And remember that the flow term, once I do my Galerkin approximation, looks like this. I multiply by Ni and integrate it over the volume. Well, I do some algebra, which is in the HGS manual, if you want to know the details. But I end up with this nice expression here. So I sum over J in eta I, where eta I is a set of neighbor nodes, node I. So for example, here's node I, and the set of neighbors nodes for node I would be all the mesh neighbors, all the guys in this would be the set of neighbor nodes of node I. So I'm summing over those neighbor nodes. And Kr, I plus a half, Ij plus a half, n+1, that's the relative permeability at time n+1 between nodes I, node I, and node J. And finally, this gamma Ij term here is what's called the influence coefficient. And that's given by this expression here, which is somewhat abstract looking, but it's easy to interpret what that means physically. And finally, of course, I have the head difference between nodes J and node I. So the final equation at node I ends up being very simple. So recall again that the mass at time n+1 delta T is just given by porosity, saturation, times the volume associated with that node. So the final discretized CVFE equations at node I are simply a mass balance. So left-hand side is just the mass at time n+1 minus the mass at time n. Right-hand side, I have sum of flows into node I from node J, and the sum of the source and sink inflows at node I, whatever they may be. Where this flow term here is just given by the expression from the last slide. So flow from J to I is gamma Ij influence coefficient, relative permeability term times the head difference. Now the volume at node I, that's kind of an abstract concept. And you remember that the volume is just simply the integral of the basis function over in the whole domain, but you can visualize this. So for linear elements on triangles, each triangle contributes 1/3 of its area to the volume at node I. So for example, here's the volume, effectively a visualization of the volume associated with node I. So each triangle here in the neighboring, which neighbors that node, contributes 1/3 of its area to that node. And again, if you want to have a picture in your mind what that influence coefficient is, it's essentially the flow area times the absolute permeability between nodes I and node J. Now, what about mass conservation? I claim that the CVFE method is mass conservative. And this is what we mean by that. I'll just state that like a theorem. If the discrete equations are solved exactly, then the CVFE method, or discretization, has exact mass balance for any time step in any mesh size. Well, the proof is actually trivial. It's got 2 lines. I'm going to sum the CVFE equations over all nodes. So I'll take every discrete equation and I will sum it over all the nodes. So the left-hand side is going to be the total mass at time n plus 1. The right-hand side, I'm going to have a term which is the total mass at time n. This will be the total source inflows over that time step on the right-hand side. And finally, here's the flow term here. Now, I cleverly wrote this flow term here using the fact that if I just sum for j bigger than I, then if I include the flow term from j to I and I to j, that will be the total flow over all the flow terms on the right-hand side. And I did that because then it's obvious. Flow from j to I is going to be equal to the negative, the flow from I to j. So this whole term here will just be 0. So I get the right-hand side then is just this expression here, which is mass at time n total is source inflows over that time step. Now, in other words, the total mass at time n plus 1 equals the total mass at time n plus the sum of source and sink terms. Now, note that any convergent discretization conserves mass as the mesh and time step go to 0. A mass conservative discretization conserves mass for any mesh size and any time step size, not just in the limit or theoretical limit as the mesh and time step go to 0. In practice, we're always using finite mesh sizes. So we're interested in what happens in the finite mesh size, not just in this theoretical limit. What about this positive influence coefficient property, which I mentioned earlier on? Well, remember that the flow between nodes J and node I is given by this expression here. We have the head difference, we have the relative permeability, and we have this influence coefficient. Well, the CVFE method requires that we should have positive influence coefficients. Why? This ensures that the discrete flows are always in the physically correct direction. So, for example, if Hj is bigger than Hi, the fluid then flows, discrete fluid flows from J to Y. If this is not true, you get rather absurd things happening. Dense fluids float on top of less dense fluids in a discrete sense, which is obviously physically observed. So again, I'll emphasize again, this positive coefficient gives us physically correct flow directions. So for example, if I have some node H, the head at some node Hi, then if the head at node J, Hj is bigger than Hi, then the fluid will flow from Hj to Hi in the obviously correct physically flow direction. And similarly, if Hi is bigger than Hk, fluid will flow from I to K. Now this positive influence coefficient condition is essentially a condition on the mesh construction. And this is not easy for complex geometries. And this is one of the things we try to do as much as possible in HGS is to ensure that our mesh construction ensures this property of positive influence coefficients. Now, what about upstream weighting? Something else I mentioned earlier on. Well, recall the flow from J to I is again given by gamma ij, and we fixed that. We made sure that's non-negative or positive. And we have the head difference term here. And now we have the relative permeability between nodes I and node J. We're going to use upstream weighting for Kr evaluated between nodes I and node J. How do we define that? Very simple. The upstream weighted value of this relative permeability is simply equal to the value at node J if Hj is bigger than Hi, and it's equal to Kri if Hj is less than Hi. Very simple idea. So why are we interested in having an upstream weighted method? And the main thing is this result here. Again, you can prove this result here, and you can refer back to a paper from 1997 I wrote on that, or one of my students. So if a CVFE method is used with fully implicit time stepping, positive influence coefficients, and upstream weighting, then the scheme is monotone. And what does monotonicity mean from the point of view of mathematics? It simply means that if I take the partial derivative of HIN plus 1 with respect to Hj, this is greater than or equal to 0. So what does that mean? Or why is it important? Well, you can kind of get an intuitive idea why that's a useful property, because if that's true, and if I look at my generic node here, node I, if I perturb the value of the head and the neighbor node j, then this will result in a positive change in the head at node I. This is physically makes sense, right? Increase this value here, then this value should increase. And the bottom line from this property is that this guarantees that non-physical oscillations cannot occur in the numerical solution. And of course, you also have the property that mass cannot go negative, which is obviously something you require. Is upstream weighting bad? Some of you have probably heard people say, well, they don't like to use upstream weighting. And why is that? Well, if we think of a linear problem, sharp fronts smear as time goes on, which is an undesirable property. However, for nonlinear problems, such as Richard's equation, saturation fronts are self-sharpening. This means the saturation fronts, they're smeared, but only over 1 to 2 cells. So it's not such a big deal. This is a small price to pay, but we would argue, for robustness. All right, now I'm going to show you some reasons why the CVFE method with all these properties actually results in a very robust technique. And here I'll show you an example of a simulation we did. I'm going to compare upstream versus central weighting. So remember, central weighting is not monotone, upstream weighting is monotone. And this is an example of a capillary barrier cover for a waste site. This is from something that people suggested to be used in areas like Los Alamos. And the capillary barrier is constructed by having a layer of loam, a layer of sand, a layer of gravel, and this is over the final crushed tuff, which is the kind of standard sort of thing that you find in the Los Alamos area. This is a simple two-dimensional, so it's vertically downward in that direction simulation. And we have a constant infiltration rate of about 15 centimeters per year. And the idea here is that you would put some waste down here somewhere, and this capillary barrier would ensure that the water flows and avoided this waste, kind of flowed through here, and finally the capillary barrier would fail somewhere down the slope here, protecting the waste in this area. So anyway, let's see what happens. So we ran this, and this time we're using upstream weighting. And again, to kind of point out the real interesting features of this simulation, we're going to use some very coarse contours for the saturation. I'm going to show you a darker, showing you the darker values here in this flooded contour grid mean lower saturation, lighter colors are higher saturation. So darker colors, lower saturation, higher, lighter colors are higher saturation. On the left is the coarse grid, and the right is a fine grid. And this is upstream weighting, positive influence coefficient, mass conservative. And you can see here, there's actually not very much difference between the coarse grid and the fine grid. In both cases, we can see, again, remember that darker is lower saturation. We can see the capillary barrier fails about 10 meters down the slope. So you're safe putting stuff there, but certainly not there, okay? So water has come in here and infiltrated, but going down here on the right, about 10 meters down the slope. So the dark area means that no water has got in there. Okay, now let's do the same thing with central weighting for the relative permeability. Again, remember that darker is lower saturation, lighter is higher saturation. Left is a coarse grid, right is a fine grid. Central weighting. Look at this. Well, we can see some funny kind of oscillations here. Well, eventually, when we make the grid finer on the right-hand side, these oscillations did tend to go away. But look at this. We also have this physically incorrect local minimum here in the middle of nowhere. And that's still there on the finer grid. And similarly, this whole region here consists of incorrect local minimum in this capillary barrier. It's completely wrong. And we find the grid, we can see it's still there. Well, it's getting smaller, right? This is definitely smaller than that, but it's going to go away at a very, very slow rate. So we're going to have to use a very fine grid to make sure that these kind of effects are small, much smaller, much finer grid than we used with upstream weighting. Again, I'll remind you, I'll go back to the upstream weighting, and you can see that we got none of this non-physical problems. Okay, so let's summarize then our final results here about this CVFE, control volume finite element method, which we use in HydroGeoSphere. So basically, we use unstructured grids, and in that way, it's very easier for us to handle things like fractures, dual porosity, overland flow features with streams and lakes. Our discretization is mass conservative. So for any mesh size and any time step, again, this is any mesh size, any time step, not in some theoretical vanishing limit of mesh size and time step. The discretization is mass conservative. We ensure positive influence coefficients when we construct a mesh. This means that the flow is always in the physically correct direction. And it's monotone. Use of upstream weighting gives us a monotone discretization. What that means is that there's no physically incorrect oscillations. There's no physically incorrect local max and min. So the bottom line here is that a robust discretization should pass all these three tests: mass conservative, positive influence coefficients, and monotone, to give you a robust technique, right? We want a robust technique. Unfortunately, you'll see a lot of methods in the literature fail one or more of these tests. So if somebody comes to you with a new discretization method, you would ask, okay, is it mass conservative? Does it have positive influence coefficients? Is it monotone? If it is, okay, that's a candidate method to be used. If not, we think this CVFE method is a good technique to use because it's very robust, very reliable, and gives you good results no matter how nasty a problem you've got. Okay, with that, I'm going to hand things over to Hyoun-Tae, who will tell you some more interesting things about HGS.
Well, that finishes Dr. Forsyth's presentation. Thank you very much, Peter. We do have one question from Derek in the chat. The question reads, with basis functions that are higher order than linear, is it possible still to guarantee positive influence matrix coefficients, or are there additional considerations aside from mesh geometry? Dr. Forsyth, did you want to take a stab at that one?
Sure. I'm going to say it's almost never possible. So in general, it's very rare that you can construct higher order basis functions that have that positive influence coefficients. You're pretty much stuck with linear type basis functions. At least that's what my experience is. And I mean, there is some possibility, but I think for a general kind of mesh, it's virtually impossible. That's my experience.
Okay, there we go. So that was the only question I saw in the chat so far. I'm going to start the next presentation by Dr. Hwang. Anybody who comes up with a question, again, feel free to pop it into the chat, and we will take some time after this second presentation to address any of those questions.
Good afternoon, everyone. Welcome to a HydroGeoSphere webinar for numerical method and parallel processing. My name is Hyoun-Tae Hwang, Director of HydroGeoSphere and Senior Hydrogeologist at Aquanty. My talk today is about more practical aspects of the CVFE method and parallel processing. As Peter mentioned in previous talk, the CVFE method is robust and reliable. If someone asks me if every simulation result will be good with the CVFE method, my answer will be absolutely no, because the CVFE method is a good tool like a nice car, but it depends highly on who is using it while driving the car. So my talk mainly focuses on why mass generation or construction is important, and how to use or drive the CVFE method to achieve better solutions. Additionally, I'm going to talk a little bit about the parallelization techniques implemented in HydroGeoSphere. Now, a brief overview of my talk is that first I will talk about mesh construction for CVFE and then parallelization. Specifically for the first part, main numerical schemes implemented in HydroGeoSphere, and then I'm going to talk Little bit about mesh construction for best practice by checking your mesh equality. And then for the second part, I will also introduce some parallel schemes applied to HydroGeoSphere, which we specifically developed for improving computing efficiency. Here is an example of meshes for 2D surface and 3D subsurface flow and solid transport simulations. This numerical model consists of 15 layers with 220,000 nodes per layer, and that comes down to 3.5 million nodes in total. This model is constructed with triangular elements for 2D surface model and prism or pentahedron elements for 3D subsurface model. You can build a 3D model with one of these three types: tetrahedrons consisting of 4 nodes, hexahedrons with 8 nodes, and pentahedrons with 6 nodes. But a numerical model with mixed mesh shapes is not currently applicable to HGS. Okay, let's look at numerical schemes implemented in HydroGeoSphere. Here, this figure shows the difference between physical and numerical domains. Physical domain represents the real system, and the numerical domain represents the simulation domain. In the finite element approach, as Peter mentioned before, the finite element method uses basis function interpolance to approximate solution in numerical domain. Problem is the basis functions are based on the orthogonal coordinate system, which is the same as the physical system. For numerical domains, if a mesh is a hexahedron with right angles, it is easy to calculate basis function interpolance because every angle in this element is orthogonal. However, in many cases, we use unstructured meshes like this to represent more realistic conditions. This case, this numerical domain is required to be transformed using this Jacobian, which is extremely time-consuming for calculation. So we use integrate finite difference approach, which is relatively simple and cost-effective. This figure shows how this approach calculates hydroconductivity for neighboring nodes. For example, when HGS calculates water flux along LIZ segment, which is not parallel to XYZ coordinate system, because this element is not orthogonal, the hydroconductivity along each direction is approximated using this relationship, which means this theta 1, 2, 3 are degrees between vector Liz and XYZ coordinate system. If this Liz vector is parallel to x-axis, then k12 is the same as kxx, because theta 2 and 3 are 90 degrees, and that canceled out y and z component. Let's look at the importance of mesh construction. For calculating influence coefficient along each segment in this triangular element, originally we used the circumcenter approach to calculate the influence coefficient for each neighboring node. In many cases, it works fine if the circumcenter is located inside of this triangular element. However, if the triangular element is something like this, which is one of 3 inner angles is greater than 90 degrees, then you can see circumcenter of this element is located outside of this element. The problem is the influence coefficient or flow area for nodes 2 and 3 is negative, which causes oscillatory behavior because of internodal flow between 2 and 3 is from lower to higher heads. So we can solve this problem by assigning 0 for negative influence coefficient. Unfortunately, we have additional problems. Here are problems related to negative influence coefficient. For surface flow simulation with zeroing negative coefficients, like here we are looking at the spatial distribution of surface water depth with blue representing shallow water and red representing deep surface water depth. As you can see in the downstream of this domain, there is a water build up in this area even though there is no dam assigned in this simulation. So because of this zero influence coefficient, surface water cannot flow at this point and generate huge water reservoir in this area. Let's look at the problem of circumcenter approach. Here at the same location, there is also a huge reservoir because of orthogonal triangle elements that causes a zero influence coefficient. In this case, the influence coefficient is also zero because the circumcenter is located on this line. To solve this problem, we implemented the inner center approach, which guarantees positive influence coefficient because the center of this circle is always located inside of this triangular element. So we can solve this problem for numerical dam related to the influence coefficient. Even though we have various numerical scheme, one thing we should keep in mind is that high quality mesh is the first priority for achieving reasonable solutions. High quality mesh can reduce numerical oscillations and improves computing efficiency. How to obtain good mesh is actually another research field, which is also related to graph theory. We don't need to get into this. Instead, we can use good mesh generator that can produce good meshes. Here, AlgoMesh developed by Hydroalgorithmics is one example. Additionally, we can also check quality of generated meshes with two things, element size and element aspect ratio. For element size evaluation, we can simply check minimum and maximum element sizes based on element size distribution of model. And next is element aspect ratio, which is a ratio of maximum to minimum edge length of each element. Okay, let's look at an example of simple mesh quality evaluation. Here we are looking at the mesh size distribution and aspect ratio distribution based on this 2D surface model only. In element size distribution, the element size of the model ranges from 0.1 to 1 million square meters. For the element aspect ratio distribution, the aspect ratio ranges from 10 to 10,000. Here we need to have closely look at relatively small elements and also relatively high aspect ratios. We are looking at meshes generated with constraints which are in red dots and lines or segments. For 2D mesh generation, these constraints are generally used for representing important geographic or hydrologic conditions such as streams, rivers, or observation points. These meshes are mostly looking good, but if we zoom into this area, we can find meshes around these constraint nodes are elongated, which causes small elements, sizes, and high aspect ratios. Using AlgoMesh optimization process, we can obtain good quality meshes. Here, these figures show the optimization process performed by HydroGeoMesh. In the first step, there are many coarse meshes, and you may notice that there are two meshes that are elongated nearby the constraints. In the second and third optimization steps, bad meshes are now disappeared by mesh refinement process. In the final stage, there is no further optimization, which the meshes are almost similar to those in the previous step. So if we look at the element size and aspect ratio distributions, we can find that there is no small element size less than 1 square meter, and aspect ratio of the meshes ranges from 1 to 4. Now move to parallelization implemented in HydroGeoSphere. Here these figures show the difference between serial and parallel computing. Serial computing uses only one core or CPU for processing data, while parallel computing uses multi-cores for processing data simultaneously. So basic idea of parallel computing is to save computing time by breaking up a task into smaller pieces and executing those pieces at the same time with multi-cores. Then let's look at parallel computing in HydroGeoSphere. We use OpenMP library for shared memory system, which is like your desktop. Here, this figure shows the computing flow of HGS, which mainly consists of three parts: initializing program, solving matrix, finalizing program. For the solving matrix part, there are two types of matrix solvers, linear and nonlinear solvers. And each of the solvers has three main parts: matrix assembly, matrix preconditioning, matrix solver. And parallel algorithms have been implemented into matrix assembly and matrix solver parts because they are the main bottleneck during integrated surface and subsurface simulations. Okay, we can look into parallel scheme applied to matrix assembly. This figure shows a generous matrix structure for serial computing. If we apply parallel algorithms directly to this matrix, there will be something like this. It may work in some cases, but there will be data racing condition which occurs when multiple cores access a shared memory location simultaneously. Here you can see the overlapped areas, these overlapped areas, which each core requires information provided by other cores. For example, core 2 in this case needs to wait for information until core 1 provides this information. So the computing efficiency will not be much improved because of this waiting time. So we need to split the simulation in simulation domain into number of cores used for parallel computing, as you can see in this figure. Here the matrix has been restructured for 2, 4, and 8 core computing using domain decomposition method or domain node reordering method. And then we can move on to the matrix solver parallelization. For improving the computing efficiency, we have developed parallel computing algorithms that are especially efficient for handling large data sets. This algorithm is called as matrix chopping and privatization scheme. For large-scale model, its matrix requires huge memory access, which takes much time to get information from shared memory system. So we can reduce memory access time by chopping the matrix and arrays. Additionally, we found it can be more efficient if the chopped matrix is stored for each core, which is a privatization scheme. So finally, using the array chopping and privatization scheme, each core can solve this size of matrix without accessing the main matrix. Okay, here is the summary of my talk. First, HGeoSphere uses advanced numerical schemes that can provide physically correct solutions. For better mesh quality, users need to check element sizes and aspect ratios before running simulations. Additionally, robust mesh generators such as AlgoMesh are recommended. Second, HGeoSphere uses efficient parallel algorithms such as matrix chopping and privatization schemes for improving computing efficiency. Well, that's it from me. Now we can move on to the question session. Thank you for your attention.
Thank you very much, Hyoun-Tae. This brings us to the end of our webinar on the numerical solution techniques and parallel processing framework that power HydroGeoSphere. Please see the video description for further resources and reading material on these topics. If you're interested in learning more about HydroGeoSphere, I encourage you to reach out to us at Aquanty and join us in our monthly training sessions. You can also find HydroGeoSphere research highlights on our blog. And of course, if you have any questions or comments, feel free to email us at info@aquanty.com.